Have you ever actually stopped and just watched things move? Like really paid attention to it? From just walking into your kitchen all the way up to the planets orbiting in space. Literally everything is in a constant state of motion. But how do we actually pin that down and measure it? How do we quantify reality itself? Well, physics is the foundational language of the universe, and today we're going to learn how to speak a little bit of it. Welcome to this explainer.
Okay, let's dive right into this. Here is our roadmap for today. We're starting with Section 1, Scalars, Vectors, and Motion. Then, we'll break down distance versus displacement. In Section 3, we're looking at speed, velocity, and acceleration. After that, we'll explore the simple pendulum. And finally, wrap things up in Section 5 by calculating the pendulum time period.
All right, Section 1, Scalars, Vectors, and Motion, the language of physics. Because before we can even start tracking a moving object, we've got to establish the basic building blocks of how we measure reality. It all boils down to two states, right? Rest and motion. A body is in a state of rest when there's absolutely no change in its position relative to its immediate surroundings. But the exact second that position changes compared to its environment, bam, the body is in motion. It's entirely about relativity and your specific point of reference. And this brilliantly illustrates one of the absolute most critical divides in all of physics, the difference between scalar and vector quantities. Think of a scalar quantity as just a pure number. It's expressed entirely by its magnitude. Take the mass of an object, like 5 kilograms. It doesn't need a direction, right? It's just 5 kilos. But a vector quantity? That requires both magnitude and direction to actually make sense. Things like force or displacement. And because vectors have that directional element, you can't just add them up with simple arithmetic like you do with scalars. You have to use an entirely different mathematical system called vector algebra.
So, the crucial takeaway here is that direction changes everything, which perfectly tees up Section 2, distance versus displacement, the journey versus the destination.
When you're moving around, are you the kind of person focused on the journey or just the destination? Because that is exactly the difference between distance and displacement. Distance is a scalar quantity. It's the total overall length of the pathway you moved, and its value is always positive. It cares about every single step of your journey. Displacement, on the flip side, is a vector quantity. It is literally just the shortest straight line from your initial starting position to your final position. And because it factors in direction, displacement can actually be positive, negative, or even zero. It only cares about the destination.
Now, this brings up a really fascinating scenario. I want you to think about this for a second. Is it possible for your displacement to be exactly zero, even if the distance you traveled is very clearly not zero?
The answer is yes, absolutely. And the perfect classic example of this is circular motion. Imagine running a full lap around a running track. You have undoubtedly covered a measurable distance. Your smartwatch will definitely confirm you ran, but because your final position is the exact same spot as your initial starting position, the shortest line between those 2 points is nothing. Mathematically speaking, your displacement is zero.
Okay, so now that we know how to measure the space we cover, we've got to figure out how fast we cover it. Let's jump straight into Section 3, Speed, Velocity, and Acceleration. How fast things change.
Just like we had to compare distance and displacement, we need to compare speed and velocity. Speed is just the distance covered per second, typically measured in meters per second. It is a scalar, just a magnitude. But the moment we attach a specific direction to that speed, it transforms into a vector quantity called velocity. So, if you say you're driving 60 kilometers per hour, that's your speed. But if you say you're driving 60 kilometers per hour north, now you're talking about your velocity.
But what happens when that velocity actually changes? Well, that is where acceleration comes into play. Acceleration is defined as the rate of change of velocity over time, and we measure it in meters per second squared. Now, if an object is slowing down, its velocity is decreasing, right? In physics, this negative acceleration actually has a specific name. It's called retardation. To put that into perspective, imagine a bullet moving at 20 meters per second. If it hits a target and completely stops after penetrating just 10 centimeters, that target has caused extreme retardation on the bullet.
Let's zero in on a very specific type of this, uniform acceleration. This just means the velocity is directly proportional to time. It's increasing at a perfectly steady, constant rate. If you were to plot this out on a velocity time graph, it would look like a perfectly straight line angled up from the time axis. And we see this all the time in nature. If you drop a pebble off the top of a tower, its speed and its displacement are going to change as it falls, sure, but the acceleration remains constant, dictated entirely by the uniform, steady pull of Earth's gravity.
So far, we've spent all our time in one dimension, dealing with straight lines. Let's see how this builds into our next topic. Section 4, the simple pendulum, from linear to oscillatory.
A simple pendulum is like the poster child for simple harmonic motion, and the absolute most important metric we care about here is the time period, represented by a capital T. The time period is simply the total time it takes for the pendulum bob to complete one full oscillation. That means it swings out from its resting starting position all the way to one side, crosses back over to the other extreme, and returns exactly back to where it started. That whole round trip is one oscillation.
So how do we actually predict exactly how long that back and forth swing is going to take? It's time to deconstruct the math in Section 5, Calculating Pendulum Time Period, the math revealed. Now, what's really fascinating here is just the elegant simplicity of this formula. The time period, t, equals 2 times pi, multiplied by the square root of L over g. In this equation, L is just the length of the string, and g is the local acceleration due to gravity. That's the whole shebang.
Okay, let's do a little physics myth-busting and look at what actually impacts the swing. Based on that formula, the length of the string has a direct effect. If you make the string longer, the time period increases. Gravity, on the other hand, has an inverse effect. In stronger gravity, the time period decreases because the bob gets pulled back down faster. But here is the real kicker. The mass of the bob, it has absolutely zero effect. Literally none. A heavy pendulum and a super light pendulum of the exact same length will swing at the exact same rate. And as long as your swing angle is relatively small, the amplitude doesn't change the time period either.
Let's actually put this into practice. Because t is directly proportional to the square root of the length, if you were to double the length of your pendulum string, the time period doesn't just cleanly double. It increases by the square root of 2 times. And what about gravity? Well, if you took your pendulum all the way up to the moon, where gravity is significantly lower, it would swing a lot slower, which gives you a longer time period. Engineers actually use these exact dependencies to invent something called a seconds pendulum. This is a highly specific pendulum design where the time period is exactly 2 seconds. It takes 1 second to swing out and exactly 1 second to swing back. Historically, this actually helped define the modern concept of a second. We have covered a ton of ground today, from the strict, rigid definitions of scalars and vectors, all the way to the incredibly smooth mathematics of a swinging pendulum. But before we go, I want to leave you with a really provocative, slightly mind-bending theoretical question straight from our source material. Based on everything we just learned about that formula, what do you think would happen to the time period of a simple pendulum if the string had an infinite length? If the length L approaches infinity, well, the time period T also approaches infinity, which means the pendulum would literally never ever complete a single oscillation. I mean, sure, it's a theoretical abstraction, but it just perfectly cements how completely reliant a pendulum is on its length. I really hope this explainer has shifted your perspective on how we measure the moving world around us. Keep questioning the physics of your everyday life, and we'll see you in the next one.